Okay, we start the last material of the course this week, and basically we're going to be working on polar coordinates. Now, immediately people get the cold chill, like, oh gosh, no, you're actually going to love polar coordinates eventually. Maybe not this semester. Next semester, they're used quite often, and in fact, if you're using polar coordinates, it's because it made your problem significantly easier. You never would choose to make a problem harder. You use polar coordinates because what you're dealing with essentially was circular in nature, and rectangular coordinates might be really, really hard to work with. And we're going to look at several examples today. So I'm going to start from scratch as if you've never done this before. Okay? I have a point here that's called the pole. In the XY world, the pole is the origin. In the polar world, there are no axes. So there's just a point. It's called the pole, and it's equivalent to the origin. Then what we have is a ray going in this direction. Think of the ray in XY world as the positive x-axis. Now, every point in 2 dimensions is a certain distance from the pole, which we'll call r, and makes an angle, we'll call theta. Okay, if I draw a line segment there. So every point in 2 dimensions, if I draw a line segment to the pole, there's clearly an r and there's clearly a theta. Let's say this theta, let's just say it's 45 degrees. Well, couldn't I go around another time? And now it's 45 plus 360? Or if I say in radians, it's pi over 4, but then I'm going to go around 2 pi again. How about if I keep going around 2 pi's? Aren't there a lot of different ways I can end up right there? Every time I add 2 pi. So representation in the polar world is not actually unique in terms of the angle. There's an infinite number of angles that are coterminal. So we usually go with the smallest representation of the angle for convenience, not for correctness. So if this was pi over 4, I could also call it negative 7 pi over 4. Yikes. I could also call it 9 pi over 4. I could call it pi over 4 plus any multiple of 2 pi. Okay, so if I have this, then I can represent every point by the r and by the theta. So now, what if I want to compare it to the xy world? Okay. So now, if this is x comma y, I'd like to be able to seamlessly go back and forth. If something's given in x comma y, I want to be able to figure out how to write it as r theta. If something's given with r and theta, I want to know how to write it in terms of x and y. It's a fairly simple notion. And once I get this, it's actually really easy to go back and forth. So let's make a little right triangle. So that would be x, that would be y, and what do you notice right off the bat? You see something there? Hopefully. Yeah, there's a nice little Pythagorean relationship there that x squared plus y squared is equal to r squared. That's convenient. How about the tangent of theta? What would that be? Tangent of theta. Y over x. That would also be the slope of that line segment, wouldn't it? Well, that is the definition of the tangent. It is equal to the slope. Now, that's nice, but now I want you to think SOHCAHTOA, okay? What is the cosine of theta? What is the sine of theta? What is the cosine of theta? X over r, and the sine of theta is y over r. This leads to x equals r cos theta, and this leads to y equals r sine theta. It's an implication symbol, not an equal sign. Never use an implication to mean equal. It doesn't. It doesn't even suggest the possibility that something's equal. It just means if this is true, then this is true. Now, this is how you go from polar to XY world. This is how you go from XY world to polar. Does this look familiar, this part here? Isn't that kind of the parameterization we were doing with t the other day? We were using t as the angle, and we said r cos t and r sine t. But that was for one parameter t. In that case, we were thinking of r as being a constant. In this case, we're not thinking of r as a constant. In this case, we're actually thinking of r as a variable, potentially. Okay, so I have two variables here, and now I have two variables here. So the polar transformation, if given something in XY world, and I want to switch it to polar, I do stuff like this, or I do this. It doesn't matter which way I go. So let's do a simple example of something where you're given something in polar, and you want to convert it to X and Y. It's far more likely that you have something in XY than you want to convert it to polar. So let's suppose I had something like this. How about, let's see, I'm trying to keep this relatively simple. Let's say we have 4 times the 4 times the cosine of theta is equal to R. Okay, I'm giving you something in polar, or I'd say R equals. It doesn't matter which way I go. So if we were in XY world and you were given an equation that you didn't recognize, wouldn't we usually do something like this? Make a little table of coordinates X and Y. Well, in this case, pretty much it's always going to be the case that theta is going to be the independent variable. You're going to choose theta and you're going to calculate R. So it's far easier if you go like this. Well, let's keep it really simple. How about if I do things like, okay, 0, let's see, I know the cosine of pi over what? What's a common angle that I know the cosine of easily? No roots, like halves. Pi over what? That'd be 0. Pi over 3. Pi over 3 is a good one, because the cosine of pi over 3 is a half. So this will give me a 2. Cosine of pi over 2 is 0. Okay. I mean, that's still important. So then if I do 2 pi over 3, then the cosine would be negative a half. And so now I'd be at negative 2, which is kind of a weird one. We'll figure that one out. And then let's say we're at pi, and now at negative 4. Let's keep going. We're doing this as if we've never done something like this before. This is just totally new. Sorry, that should go 4 there. Now, what would the next one be? 4 pi over 3. I'm in the third quadrant here, so that's a negative 2. 3 pi over 2, I'm back to 0. 5 pi over 3, now we're this again, and then 2 pi, we're back to 4. So I would like to plot this. Now, the plotting of it's a little bit on the tricky side. Okay, if I'm going to plot this in XY, ooh, how do you do it in XY? Well, one way of doing it, I'll show you. Some of you may have seen this before. How many have seen this, a picture like this before? In what context? Maybe physics? Yeah. It's called, you've seen polar paper. Polar paper is a series of rings where you might have the grid, the vertical and the horizontal in the background. They're not the dominant, the rings are. So think of everything on the circle as radius 1, radius 2, radius 3, radius 4. And then you might see things like this, you know. You'd see the rays. Now in my case I said pi over 3, so I was using pi over 3 types. So maybe that one, and maybe that one. We're going to do a couple of examples of this. So when I'm at 0, I go 4 units. This is actually not that hard to do. When I'm at pi over 3, which would be this one, I'm 2 units, which puts me right on that circle. When I'm at pi over 2, I'm 0 units, so I'm right here. When I'm at 2 pi over 3, r, which would go this way, is negative 2. What do you think I should do if I'm on that one and r is negative 2? See, when r was 2, I went this way. But if r were negative 2, maybe I should go the other way. So I'm going this way, negative 2, so that would put me down here. And then I get to pi, but I'm negative 4. Oh, I'm back to here. Huh. Okay, 4 pi over 3 that's here, I'm -2. Oh, I'm back to here. I think I'm retracing my steps. 3 pi over 2, I'm back to 0. 5 pi over 2, I'm 2. Oh, I'm already there. So do you see that we just reproduced half of this? What the heck? What the heck is this? I want to guess. What do you think it is? I kind of tried to.
It's an ellipse.
Is it supposed to be a
Circle.
Oh.
How the heck we're supposed to get a circle out of that? And it's a circle where I actually went around 2 times. Huh. How in the heck? Oh, but what if I use this? I can't convert cosine of theta to anything. I can't easily convert r to anything. Can I multiply both sides by r here? It's a trick question. I want to. Can I? Ooh, this actually is a very important question that I'm going to show you right now. All right, I've probably done this before. Pretty sure I've done this in this class before. Okay. X equals 2.
Okay.
You ever got it? Any question? All the hands go up at this point, right? X equals 2. Now, the multiplication property of equality says if you multiply both sides of an equation by the same non-zero value, you will preserve the equation. The addition property says if you add the same thing to both sides, you will preserve the equation, and that's generally how we always solved algebraic equations. We manipulated them by adding and multiplying. Sometimes we might square both sides. Sometimes we might take a logarithm of both sides. But as long as what I did preserved the equation, I can manipulate. So just for the heck of it, let's multiply both sides by x. So then I get x squared equals 2x. Okay, great. Now I'm going to add -2x to both sides. Okay, so I know that's true. Now I'm going to factor. Well, that's pretty easy. So this means that either x is 0 or x is 2. Okay, great. But there's a problem.
It doesn't only work for multiplication, it doesn't work for addition and subtraction.
Well, no, there's the addition property of equality and the multiplication. Multiplication has a condition, addition doesn't. If you and I make the same amount of money and we both are given a $100 raise, we're still going to make the same amount of money. Right? We're not going to lose that. If we're given different amounts, then we would lose that. If you and I make the same amount of money and both of our salaries are doubled, we'll still make the same amount of money. That's the multiplication. Okay, what's the problem? I said x is 2, period. How did we grow a 0? Because we did the most illegal step that's humanly imaginable. And that's the question I'm asking. Is it legal to multiply both sides by r there? The answer is maybe. Where did this come from? I did an illegal step. Anybody see it? I think I've done this before with you guys.
Because you're multiplying by 0.
It's right here. I multiplied both sides by a variable. You can never do that, period. That's an absolutely illegal step. Remember, the most absolute rule that you cannot violate is you can never multiply or divide by something that can potentially be 0. And I just multiplied both sides by x, which can be 0, and therefore I introduced an extraneous solution. Yikes. Similarly, baby algebra. Remember doing stuff like this? Now the domain of this is all real numbers except what?
-1.
-1. But if I factor and cancel, which is what I should be doing, because it will be easier to work with, then this would equal x minus 1, which gives the illusion that my domain has now changed to all real numbers. A domain cannot change. So even in remedial algebra, what did you do at this point? I call it the disclaimer.
X does not equal -1.
Yeah. This is equal to this as long as this is true, because I just divided by something that could potentially be 0, which means I lost something. Now, this is, you can't multiply both sides by x. Didn't you have problems even in baby algebra where you were given quotients of rational quotients, and you had to multiply through just in order to solve it, but sometimes you introduced extraneous solutions? So when you multiply through by something involving a variable, you then put the disclaimer saying you can't be that thing. So let's go back to here. I really, really want to multiply both sides by r. Because if I multiply both sides by r, this will be easy to solve. I can only multiply both sides by r if r equals 0 was already a solution. I cannot multiply both sides by x because x equals 0 was not a solution, and therefore I created a new problem. Is r equals 0 a solution to this?
Yes.
Yes. So by multiplying both sides by r, am I changing anything? Am I adding anything to the problem? No. So therefore, it is legal to multiply both sides by r. You say, well, would it ever not be legal? Yeah. What if I add something? Oh, what if I made that 4 cos theta plus 10? You know, just for fun. Well, that's never going to be 0, is it? But if I multiply both sides by r, I will completely change what this thing is. It will not be the same thing anymore, and that would be an illegal step. But because r equals 0 is possible, you know, pi over 2, 3 pi over 2, several places, this is now legal. So why would I want to do something so crazy as that? Well, because what's the left side? That's 4x. What's the right side? Ooh, I think I know what to do with this. I'm going to work this way. So what if I rewrite that as x squared minus 4x space plus y squared equals 0? Is that a true statement? Anybody got any ideas? What do you want to do here? Complete the square. Ooh. So this would be what? X minus 2. So what's going to go here? 4. 4. Does not look like the equation of a circle? A circle with what center? 2 comma 0, and what radius?
2.
That was 4, 0, right? 2 comma 0, radius 2. Is it the same circle? Yeah. What would have been easier, doing it, manipulating the equation, or doing it by trying to plot points? Trying to plot points is very iffy. I almost had to get lucky to have enough points where I could see what was going on. So no, this is simply a circle of radius 2, and it completed its whole loop, by the way, just from 0 to pi, didn't it? Huh, that's interesting. It completed its whole loop, just going 0 to pi. So now, our goal today is to be able to not draw things, but describe them and manipulate back and forth. Some things you have to draw because you don't know what they look like, right? You have to actually plot some points to figure out what the heck's going on. But this one's fairly simple. R equals 2. There's no theta in there. Well, if I made a table of values, here's one way of doing it. Now, think XY world for a moment. In XY world, if I said, let's say, y equals, 6, and you wanted to make a table of values, what x values would you use? Yes. -4, 0, 5, 10, doesn't matter. And what's the y value every time?
6.
And so when I go to plot these, what am I going to see? A horizontal line. Do I need to plot points to see that? No, but if you're in a remedial algebra class, you may need to kind of figure out what's going on. Oh, it wouldn't matter what value of x I chose, y would always be 6. So, what thetas do you want to use? How about 0, pi over 2, pi, 3 pi over 2, 2 pi? Okay, great. Now what's r going to be? 2, 2, 2, 2, 2. What's this going to be? It's going to be a circle of radius 2. Where's it centered? Where?
At the origin?
At the origin. Because in this direction, I'm going to go 2 units. In this direction, I'm going to go 2 units. In this direction, I'm going to go 2 units. In this direction, in other words, in every direction, I'm going 2 units, right? I'm gonna have a circle of radius 2 centered at the origin. So one of the most important results and one of the most useful is r equal a constant is a circle. That makes it really convenient. Okay, what if I changed it to r squared equals 4? Would that be the same graph?
Well, because now you have -2.
No, because what happens if r is negative? It just means you go the opposite direction. So if you said, but if r is -2, well, then I'm just here. I'm still getting the same, I'm on the same circle. But if I squared both sides and said, okay, r squared is 2 squared, but isn't r squared x squared plus y squared equal, oh, that's my ODA. Right? That's as circle as a circle can get, isn't it? So r equal a constant, have that one in your back pocket. That one's really, really useful. R equal a constant is always going to be a circle centered at the origin with that particular radius. Okay? What if I have something like this? Oh, actually, I'm sorry, equals, wait, do I want to do 3? Hold on. No, I'm gonna do, hold on, I'm gonna tweak this, I'm gonna make this uglier, hold on. I'm gonna make that one 3R. Oh, now it's really awful. Oof. Now, we could make a table of values right now. Problem is our table of values are very limited. You know a lot of secant, well, you know cosines. But don't I run into a problem like it, pi over 2, 3 pi over 2, because cosine would be 0, so the secant would be undefined, and ooh, man, this is not very friendly. There's going to be values of theta that I can't use. Well, let's try a couple. This, by the way, this is not the best way to go. But if I don't know anything else, it's what I gotta do. So how about theta is 0? Let's use pi over 3 like we did before. Those are some gimmies. So the secant of 0 I know is 1. Okay. So that would mean r is a third. Secant of pi over 3 is 2 because the cosine is a half. So that would be r is now what, 2/3. That's really helpful so far, isn't it? Can't do pi over 2, darn. So what if I do, could I do a negative angle? Yeah, because secant is positive in the 4th quadrant, so how about if I do negative pi over 3? Then this is still going to be 2/3. That's horrible, but I think I have enough. Said this is not the best way to go, but it is a way. I'll say this is 1 unit. That's 1 unit right there. Okay, so when theta is 0, I'm 1/3. About right there. When theta is pi over 3, I got to do this twice, so I'm about here. Okay, and then when theta is negative pi over 3, I got to do that. Oh, it should be exactly the same thing. Huh. These kind of feel like they're lining up, don't they? That's kind of weird. Could I multiply both sides by the cosine? Remember, this is already as a problem at pi over 2, so it's still going to be a problem. Can I multiply both sides by cosine? If I did that, what would I get?
1 is equal to r, 3r cosine theta.
Well, what's that?
3.
Oh, wouldn't that be the same as saying x equals 1/3?
Yeah.
Which is what we just had. Not the most efficient way of doing it by plotting points. Manipulating the equation and using, oh, that's why, pi over 2 did not produce any points because this is going to be a vertical line anyway. Okay. Wow. So I can actually have lines in polar world. Now, most of the time we think of polar as being anything circular or related to circles. And it could be ellipses, could be other things. But if I have something that's circular in nature, it turns out polar's easier. And here's why. Today we're going to do derivatives later on, but next day we're going to integrate. So I'm going to find areas bounded by things. To integrate something that's circular in nature, we already know is going to be kind of tricky because circles aren't functions in the xy world, but they are functions in the r theta world. Just like they are functions when we parameterized last week. So there's some advantages to switching things to polar. Okay. Any questions so far? Keep going. So this going back and forth, not the worst thing. So I want to do another one because we're going to analyze this graph a whole bunch. The next one we're going to do, I want to draw it so we can describe it, and then describe anything similar. We're going to do derivatives to figure out what the slopes of tangent lines are at various places around it, and then next day we're going to integrate to figure out what the area is bounded by. So this is actually considered a pretty important shape, the next one we're going to do. Let's suppose we have r equals, let's say 4 plus 4 sine theta. Now, I could try to convert this to xy. Real quick check. If theta is 3 pi over 2, then the sine of theta would be -1, and the value of r would be 0. So would it be legal for me to multiply both sides by r here? Yeah, that's why I just said that. By the way, if that was bigger than 4, then a no. So if I multiply both sides by r, I get this. Oh, so let's look at it in xy world. So now on the left side, I have x squared plus y squared equals 4r. I think the only thing I can do is write that as square root of x squared plus y squared. Okay. Plus 4y. Okay. So whatever this is in polar, this is what it is in xy world. First of all, is this a function in xy world? Is it a function? No, that y squared. Would that be an easy derivative to take, by the way? Or would that be like an absolutely evil implicit differentiation problem? Yeah, I think that would be like, that'd be a really high level of evil. I mean, that's not a subtle evil. This would be awful. If I said, okay, everybody, let's differentiate this. You know, change your major, run for the hills. No. We're going to manipulate the polar, but this is what it looks like in rectangular. I don't want to mess with it. This is horrible. This is nasty. Oh, by the way, we're going to integrate to find the area bounded by this. Good luck. No, let's deal with the guy on top. So what we're going to do is we are going to make a table of values, and then we're going to plot some points, and I'm going to do my polar paper again. Because the point is, I want you to be able to recognize what this thing is. Not memorize it. No. Recognize it because it has similarities. If I had made this a cosine, or I had changed the plus or minus, it's the same shape, it's just in a different place. Maybe rotated, maybe upside down, you know, that kind of thing. So, what sort of values do we want to use? Well, let's use a lot of our common angles. So with the sine, it's the pi over 6 angles that I want to use, because the sine of pi over 6 is a half. Sine of pi over 3 is root 3 over 2, and I can use that, but it's harder for me to plot irrational coordinates. So let's go with 0, pi over 6, pi over 2, 5 pi over 6, pi. 7 pi over 6, 3 pi over 2, 11 pi over 6, and then 2 pi should have us back to the start anyway. So sine of 0 is 0, so r will be 4. Sine of pi over 6 is a half, so r would be 6. Sine of pi over 2 is 1, so r would be 8. Sine of 5 pi over 6 is a half, so r would be 6. Sine of pi is 0, r is back to 4. That's why I chose these angles, okay? Because I want easy numbers. I'm lazy. 7 pi over 6, the sine would be negative a half, so my r would be 2. At 3 pi over 2, sine would be negative 1, so r would be 0. Oh, back to the origin somehow or another. 11 pi over 6, sine is negative a half, so I'm back to 2, and then here we'd be at 4 again. Okay? So, I do not want anybody here to go out and buy polar paper, but to try to draw this on an XY plane first of all, you're estimating your angles, and then, you know, go out at this angle exactly 2 units, but how do you do exactly 2 units if you're going off at an angle? You see, that makes it a little bit trickier. So instead, I'll do my, they're not perfect, but they're close enough. All right. 1, 2, 3, 4. Stop. Now, pi over 6 is about, let's say, it's about that. And so these lines here correspond to the angles that I'm going to use. And my circles, radius 1, radius 2, radius 3, radius 4. Now I'm freehanding this. Polar paper is probably going to be slightly more accurate, only a little more accurate than my freehanded graph here. But this is now going to be really, really easy for me to draw. So at an angle of 0, remember the pole and the original ray, that angle is 0. So you're on here. Okay? Let's do this. Let's make each one of these rings 2 units. Otherwise, I got to draw 8 rings. Everybody okay with that? It'd be a little bit hard to work with because I need to be able to move that far. So if each ring is exactly 2 units, then this would put me here. Pi over 6 puts me here. Pi over 2 puts me here. And where are we now? 5 pi over 6 puts me here. Pi puts me here. 7 pi over 6 puts me here. And 3 pi over 2 puts me here. 11 pi over 6 puts me here. And then 2 pi puts me back to here. I've got everything there. Now, it might not be obvious, or maybe it is. If I do it without now, I'm hoping you've done this before in either trig or pre-calc. How many have drawn something like this before? What does it look like? Well, what does it look like? That's not what it looks like. Looks like a heart. So it's called a cardioid. Yeah, a cardioid doesn't have a cardioid means literally heart-like. Oh, that physical object looks like a cardioid. No. You'd say it looks like a heart, so it's heart-like. It's called a cardioid. I've had people call it other things over the years, but and for the purposes of what we're doing, some people just refer to it as the butt. Okay, I'm okay. Because we got to find areas and we got to find angles and things. It's called a cardioid. It's the form that I'm interested in. So if I replace sine with cosine, if I replace the numbers, but if those numbers are the same, it'll always be this shape. If I had made that a minus, this would be upside down. If I had put it as a cosine, it'd be sideways. But it's a cardioid, it's a heart-like shape. So it's not a function, but it is something that we actually can easily deal with. Next day, what we're going to do is do things like, what's the area of this thing? Or if I intersect it with a circle, what's the area bounded by the two, or the area outside of one? Some pretty cool questions. Today, I want to be able to draw it and interpret it because we're going to do derivatives in a moment. So if I gave you any angle between 0 and 2 pi, and it would probably be a common angle for convenience, could you tell me the slope of the tangent at that point? At any point on here. Can you tell me where the horizontal tangents are? Can you tell me where the vertical tangents are? Clearly I have both, don't I? So we want to be able to figure out all of these things. That's the second part of class today. That's the calculus part. So the first part is being able to manage. Now, if I gave you something in polar, you're probably going to leave it in polar unless you thought it was a circle or a line like we did a moment ago. More often than not, though, you're given something in polar and you're saying, I don't know what this is. It doesn't look like anything else, so just leave it alone. If I was given something in rectangular and I saw x squared plus y squared as part of the problem, I saw an x squared plus y squared maybe to a power. Maybe it's the square root of it. Maybe I'm cubing it or something to that effect. I would probably change that to polar, and now I just have r to a power, which would be so much easier to work with. Okay? So the back and forth is really, really important right now, just for identification, nothing else. Okay? Questions so far? Everybody cool? All right. Let's keep going. Let's see. Got this. What if, I'll do a simple one. That's a phase. These are all thetas. No fees in this world. I'd like to know what this looks like. Well, my R's are going to be small, aren't they? They're all calculated, are all going to be between -1 and 1. Now remember again, a negative value for R just means go that far in the opposite direction. Give you a really simple question. Let's pick a point like this. This is 1, 1 on the XY plane. Can you give me an R and a theta? We don't usually do a lot with points. We usually do more with the actual curves themselves. But if I wanted to convert this to R and theta, then what I need to do is figure out what is that angle and what is that value. Well, first of all, what's the R? √2. So could I say this is R equal √2, theta equals pi/4? Would that be correct? So some people will write it as an ordered pair. I'm not a big fan of writing it as an ordered pair because it now looks like I'm saying x comma y if I write it. No, I'm saying r comma theta, and as long as there's no ambiguity, I'm writing the r comma theta, or you can write it that way. Can you give me a different theta? So if I wrote it in this form, in our theta world, we'll say that this is acceptable. Can you give me a different theta? I'll be lazy. How about pi/4 plus 2 pi? Would that be the same thing? And how many of those could I write, by the way? Infinitely many. Ooh. Can you give me a different R?
Yeah, you can make R -√2 and rotate the pi by
5 pi/4, good. 5 pi/4 is this way, so I want you to go this direction, -√2 units. Oh, that's what it means. So I have an infinite number of representations of the same point in polar world. That can be confusing. So that's why we usually agree, let's pick a positive value for R whenever possible, obviously, and let's pick a theta that's small, right? The smallest theta that's convenient. So pi/4 plus 2 pi, that's obviously a more convenient theta. But if I'm in the fourth quadrant, let's say I'm 45 degrees in the fourth quadrant, I can say 7 pi/4, or I could say -pi/4, and both of those would actually be convenient, wouldn't they? So you'd have a choice at that point. Sometimes, if you remember going back to trig and pre-calc, it'll say, give me the answers, and theta is between 0 and 2 pi. You're given very specific guidelines. Okay, then no negative angles. But it is actually more practical if I use negative angles because I know inverse trig functions, like inverse tan and inverse sine, are -pi/2 to pi/2. They're defined using negative angles out of convenience, so I have one continuous interval. So the angle you choose is not unique as long as it gives you the same place. So we say these are coterminal because they put us at the same place. So just be aware that it's not always the same thing. Now, when we're doing things later, like limits of integration and stuff, we have to have the smallest interval possible. If I wanted to find the area of a circle, I'd say 0 to 2 pi. Could I say pi to 3 pi? Could I say -pi to pi? Yeah, every interval that's 2 pi long would be legal. I can't say 0 to 4 pi, because that means I went around twice, and I'd get a number that's too big at that point. Okay? All right, now let's look at the calculus. All right, so let's remind ourselves what we did before. X is a function of t, y is a function of t. Then we proved that dy dx is dy dt over dx dt, right? This is something, and we used this, and it's very, very convenient. We're going to change it a little bit, but it's going to be a little bit confusing because in xy world, we have two variables. One is dependent, one is independent. Here, t was my independent variable, but both x and y were dependent. So I technically really have three variables there, x, y, and t. But now we're going to polar, so I now have four variables, x and y and r and theta. So if I'm going to go from xy world to r theta world, I need a dependent and an independent variable in r theta world. Otherwise, we won't be able to do this. So I said, generally speaking, we always say r is a function of theta. There can be exceptions, but in xy world, we always say y is a function of x, right? It is possible to switch that, but it's not very common, okay? And it does make formulas and things a little bit trickier. So if I said r equals actually r of theta, okay? Now I'm going to define x to be r of theta cos theta. And y is going to be r of theta sine theta. So in a sense, I'm now treating theta like I did with the t, meaning x and y are now basically functions of theta. Okay? So let's find those derivatives. So I would like dx d theta. Okay, that's straight up product rule. So r times the derivative of cosine would be what? So it'd be negative r sine theta. By the way, it's understood that r is a function of theta. You don't have to write r of theta. You can just write r. In xy world, we're always assuming y is a function of x. Agreed? Do you ever write y of x? No, you just write y. It's understood that it's a function of x. So I'm saying I'm interpreting it this way, for the purpose for derivatives. But when I write it, you just write the r. That's first times derivative of second plus what? Cos theta times dr d theta. Ooh. Okay. dy d theta. First times derivative of second plus the second times the derivative of the first. Okay, so now I can say with certainty, I'll write it over there because I'm going to need the space. If I'm given something in polar coordinates, but I want the slope of the tangent, because eventually I have to draw it on the xy plane. It's going to be this quotient right here. R cos theta plus sine theta dr d theta over negative r sine theta plus cos theta dr d theta. And we would simplify this usually, if we can. Okay? So let's do a few. Let's take something we've already looked at today. So earlier I gave you a circle. I said, what did we use? We used r equals 4 times the cosine of theta. That was the first one I drew, right? That was the circle centered at 2, 0 with radius 2. I'd like to find the slope of the tangent line at every point on the circle. Okay? So let's start with, what's dr d theta? I'll show you the order of things you really want to do here. What's dr d theta?
Negative 4 sine theta.
How about negative 4 sine theta? You guys are thinking too much. You're just taking the derivative of cos theta. Okay. That's the only derivative I actually have to take. The rest I get to just write down the function. So, what is dy dx? Well, let's see, r times the times the cosine of theta plus sine of theta times dr d theta over negative r times the sine of theta plus the cosine of theta times the r d theta. That's my derivative at every point. You think I might be able to manipulate this somehow or another? Maybe make it less scary? Well, let's see, on top, if I factor out the 4 on top, I'd be left with cos squared theta minus sine squared theta. If I factor the 4 out on the bottom, how about if I factor the negative 4? Better yet, I'm going to factor out, I'm going to factor out negative 4 on the bottom, then I'm going to have sine cos plus sine cos. Do you see anything there? Well, I'll cancel the 4 first. That'll be mine. Okay, good. Is that a double angle formula? So what's the numerator? Cosine of 2 theta. Sine 2 theta. Ooh, I like where this is going. So this is just negative cotan 2 theta. Does that feel like we've seen this before? Cotan 2 theta? Didn't we do that with the rotation of axes? Didn't that show up somehow or another? This isn't a rotation of axes, but must be a fairly common term. So I can say with certainty, and now we'll check it out, that at every point on that graph, I can tell you the slope of the tangent line. But this isn't xy. I can make it xy, but I probably don't need to. So, what did we say? It was centered on the x-axis. So, how if I go like this? Okay, so is this the graph of? Okay, and remember we worked it backwards to figure out the equation. All right, so give me an angle. All right, give me a common angle. How about pi over 4? So how do you ask the question? Because I want you to get used to the proper notation. I would like to ask the question, what is the slope of the tangent line of this graph at pi over 4? We'd say it like this. This always means evaluated at. So what would this be? It would be negative the cotangent of what?
Pi over 2.
Negative the cotangent of pi over 2. What is the cotangent of pi over 2? Isn't that 0? It is. 0. How could that possibly be 0? Because if I go an angle of pi over 4, that's going to send me, it's going to send me right to there, isn't it? So that's the answer I really should have gotten. I didn't realize that's the answer I should have gotten, but that's what it is. Oh, okay. What if I want something over here, maybe? Something here-ish. Well, I'd have to use a different angle. So just for fun, let's pick like pi over 8. Pi over 8 is a really small angle. Okay? So pi over 4, pi over 8 would be half of that. Just for fun. What would dy dx at theta equal pi over 8 be? Well, that'd be the negative cotangent of what?
Pi over 4.
To pi over 4.
So pi over 4. Ooh, well what's the cotangent of pi over 4? The same as tangent. 1. So this would be negative 1. So if I went at an angle that's exactly half of this, I'd have a slope of negative 1. That's kind of cool, huh? I mean, we could do this for every angle. But that's not my goal. My goal, I really would like to know, where are the horizontal and vertical tangents? That's actually a more important question. I can give you angles all day long, and all you do is plug them in and give me an answer. That's pretty exciting stuff. Do you agree? You know, just calculate, 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 give me an answer. Okay. And we'd be dealing with things that are easy to work with, generally speaking. Let me erase this. But I would like to know where the horizontal and the vertical tangents are. So, well, the horizontal tangents will be wherever the derivative is 0. Agreed? So I need the derivative to equal 0. Well, a quotient can only equal 0 where the numerator is 0. So I'm not as interested in that as I am maybe in that or even in that. Or I could even go back to here. That would be easier. So when is the cosine of 2 theta equal to 0? Well, when's the cosine 0? Isn't it at pi over 2 and 3 pi over 2 type of angles? And we want, by the way, as a general rule, we only want angles between, let's say, 0 and 2 pi. Because if I give you a position and then I give you the infinitely many representations of that position, that's not helpful. I'd like to know exactly how many places. So let's just say at an angle of 0 we get an answer, but we also get it at 2 pi, 4 pi, 6 pi, 8 pi. I don't say there's an infinite number, I say there's one position. So let's just take one simple angle. So when is this true? Well, this is true whenever 2 theta equals what? Pi over 2 plus k2 pi. Is that a correct statement? Is that true, first of all? So therefore, whenever theta equals, take half of those, pi over 4 plus k pi. Ah, so between 0 and 2 pi, how many places is that?
2.
Just 2. It'd be pi over 4 and then 1 k past that. Or I should say 1 pi past that. Is everybody okay with that? By the way, this is for every infinitely many position. And I just said, let's just pick the ones between 0 and 2 pi. So would you agree that horizontal tangents, when theta is pi over 4 and 5 pi over 4? Oh, I'm sorry, 5 pi, theta is 5 pi over 4, sorry. So theta being 5 pi, technically I should do this. Theta is 5 pi over 4. Did we say that right? Theta is 5 pi over 4. I think we got one less answer though. Oh, no, we have a boo-boo. We were only getting one position. Because 5 pi over 4 gave us a negative r. I'm going to just put it back here. We have a boo-boo. Anybody catch it? It's not plus k2 pi.
That's plus k pi.
Plus k pi. Because pi over 2, 3 pi over 2. Oh, so this would then be what?
K pi over 2.
So we actually have... So think of this as 2/4. So 3 pi over 4, 5 pi over 4, 7 pi over 4. But 2 of these are redundant because they give me negative r's and just put me back to the same position. But those are the angles that actually do it. So this would be 7 pi over 4. 3 pi over 4 would be here, but it would give me, if you go back to the original curve, it gives me a negative value of r, which just puts me right back here. 5 pi over 4, which is here, gives me a negative value of r, which just puts me back to here. Does everybody catch that? So yes, there are technically 4 angles, but there's only 2 positions. But those 4 angles are correct. Yeah, for a moment there we were only getting 2 and like, wait a minute, something not quite right. Now let's do the denominator. I'd like to know where there are vertical tangents. Now some of you could argue, well, can't we just go with the graph itself and just look at the accuracy of the graph? And that demands that you always draw a perfect graph before you do any calculus. That's not where you want to go. You think that's going to work with the cardioid? I'm going to guess where those are. No. No, you do the calculus and then you look at your graph and say, do they match? Yeah, it's a lot safer doing it that way. So for the vertical, okay, I now need to know where is the sine 2 theta equal to 0. Well, sine is 0 at 0 and every multiple of pi, correct? Sine of pi, sine of 2 pi, sine of k pi. Every multiple of pi, sine is going to be 0. So that means that my 2 theta is going to be k pi. So my theta is going to be k pi over 2. So now if I'm sticking between 0 and 2 pi, how many angles will this give me? 0, pi over 2, pi, 3 pi over 2. I'm not going to write 2 pi because that's back to 0 again. So these are the ones. So let's see if that works. When theta is 0, I am right here. Aha. Love it. When theta is pi over 2. Did I get, hold on. Make sure we got that right. Theta is, yeah, when theta is pi over 2, cosine is 0. And I'm right here. When theta is pi, the cosine is -1, and that puts me
All the way
back to here. And when theta is 3 pi over 2, cosine is 0, puts me back to here again. So there's only 2 positions, right? What are the 2 positions? 0 and pi over 2, these just put me at the same place. Now there are 4 solutions, but there's only 2 positions. So I clearly have 2 vertical tangents, but any of these 4 angles would have put me there. Okay, so these 2, in other words, both put me here. The other 2 put me in the other position. So I found these algebraically, which is actually a lot easier than trying to do it by drawing the picture, because it meant I had to have a perfect picture. And if I have to think of Calc 1 for a moment, you want to find the slopes of tangent lines of polynomials. You're going to have to draw a perfect picture before you can find the slope of a tangent line? No, you just took derivatives and set them equal to 0. It's much easier. But then you hopefully drew a picture that said, now, does my picture match my calculus? And if it does, then you know you probably did it all right. Our picture matches our calculus. But it's probably easier to do the calculus first. Okay? So now let's look at something a little more complicated, like the cardioid. Okay. We'll do the one we just did a moment ago, which was 4 plus. We did plus. Okay, I would like to find the general derivative dy dx. Leave it in terms of r and theta. Don't even bother trying to change it to xy. That'd be nightmarish. Then I want to be able to find the slope of tangent lines at various values of theta, like we just did with the circle. And then lastly, I'd like to figure out where are the horizontal and vertical tangents in general. Okay, that's more work because that means I have to solve something. If I just give you values of theta to plug in, there's no solving. Right? You're just sticking them into a formula and cranking them out. That's the easy part. So what should I do first, you think? Look at the formula for the derivative. There's only one thing I have to calculate first, and what's that? dr d theta. And then I can just write down the answer. Now, it's going to require some major simplifications, but we'll be able to write down the answer simply enough. So, dr d theta is what? 4 cos theta. Okay. Again, I want to point out the reason we're doing this, it will make some problems in 2-dimension easier. That's true. We haven't had a lot of circular things so far in calculus because circles aren't functions and they're not real convenient. But it turns out they show up quite a bit, and especially in 3D. Spherical things, in other words, not just circular things. And it's difficult to impossible to do the calculus in 3D of things that should be converted to polar. There's no logic to trying to do things. A moment ago when I rewrote this in XY world, was that scary? x squared plus y squared plus the square root of x squared plus y squared plus something with a trig function. No. You would not want to do that. It would be so difficult. So now, if I write dy dx, so let's put everything in here. So r cos theta plus sine theta times the derivative all over the negative of r sine theta plus cos theta times the derivative. This is the derivative for every theta. Now, just sort of the general rule, when you're asked to evaluate, you're only going to use common angles, pi over 4s, pi over 3s, pi over 6s. There's no real logic to using something that's not a common angle because you won't be able to give me a specific value. If I ask you for the cosine of pi over 3, you can tell me. If I ask you for the cosine of pi over 7, you can give me a decimal approximation on your calculator and you won't be able to interpret that answer. So we generally will limit it to common angles so that it makes more sense. But I got to simplify this. I've got to solve. That looks kind of big, doesn't it? So let's go ahead and distribute on top. So I'm going to have 4 cos theta plus 4 sine theta cos theta plus 4 sine theta cos theta. Okay? All over negative 4 sine theta minus 4 sine squared theta plus 4 cos squared theta. Now I can certainly manipulate my double angles. I see them in there clearly. I can manipulate those. So that's not a bad place to start. I put that stuff together. Okay. What is that? Well, it's 8 sine theta cos theta. Is there a double angle formula there?
4 times 2 sine squared and sine theta cos theta.
How about that? Will that work? And on the bottom, isn't that just 4 cosine of 2 theta? That's an ugly theta, I know. Now let's get rid of those 4s. So now my numerator is cos theta plus the sine of 2 theta. My denominator is negative sine theta plus cosine of 2 theta. So in terms of what is the derivative, this is probably the simplest, not the best, but the simplest representation. So if I gave you an angle now, could you calculate the slope fairly simply? Yeah, it'd be easier than doing it from here. Because do you realize how many places you'd have to plug in your theta? That'd be a lot of calculations. Not that this is short, this is just a lot shorter. So let's find dy dx at, let's say, theta equals, pick a nice angle, pi over 6. Okay? So I'll go back to my picture. Okay, that's really lopsided. Sorry. That's still not very good. It's hard to freehand these things. Okay, so at pi over 6, I'm in this, generally in that sort of direction. What is the cosine of pi over 6? That's the long leg of the 30, 60, 90. Should you know that one? Actually, yeah. To be honest, you actually should know every trig function of every common angle, because it's either going to be a 45, 45 or a 30, 60, 90, and so you don't have a whole lot of options. So what's that one? Root 3 over 2. Okay. 2 times pi over 6 is pi over 3, and the sine of pi over 3 is the same value, isn't it? Ooh, that's awful. Okay. That's a 3. Okay? The sine of pi over 6 is a half, so that should be negative a half. This will be the cosine of 2 times pi over 6, which is the cosine of pi over 3, which is positive a half. And Houston, we have a problem. What is it?
Oh, 0.
It's undefined. Well, how could it possibly be undefined? Oh. That's actually what it should be. I have a vertical tangent there, don't I? Ooh, now we're gonna figure that out later. But we figured it out because we just calculated the slope and the slope was undefined. That's kind of cool, huh? I mean, it didn't give us something completely whacked. Not completely crazy. All right, let's try another angle. Let's try a safer one. How about pi over 4? Let's find dy dx at theta equals pi over 4. I think that one would be safe. Yeah. So cosine, I'm looking at this function, this formula right here. Cosine of pi over 4 is root 2 over 2. The sine of 2 times pi over 4, so the sine of pi over 2 is 1. Negative the sine of pi over 4, so that'd be negative root 2 over 2. And the cosine of pi over 2 is 0. Can I make this prettier?
Yeah.
What do you want to do? We're going to do all sorts of things that are completely inefficient, and in 10 minutes will be probably something so ugly we don't recognize it. Or just do the easy thing. We're calculus people. We never want to take the easy way out. No, that actually is, it should actually be that fast. Right? -1 over the reciprocal of this. Oh, I'm sorry, that's a minus, isn't it? Minus. So, how big is that? It's about roughly -2.5. What do you notice? Semi-steep downhill slope. In the wrong direction, right? So does that match our calculation, more or less? Yeah. What would be a problem? Tell me what a problem would be. Because I'm pretty sure that's where I'd want to be on my graph. If that was positive, or 0, or that really wouldn't match, would it? But that kind of matched. So I could give you angles all day, you could do this all day. Do you think you're eventually going to guess the angles where it's horizontal and vertical? Maybe. What if an angle where it's vertical or horizontal ends up being like pi over 8 or pi over 12? Remember, we did a problem just a minute ago with pi over 8, and we were able to do a nice calculation because of the 2 thetas. Oh, yeah. So maybe trial and error until we get all the answers is probably not the best route. So we should probably just go back to here and set numerator and denominator equal to 0 individually. You with me on that? Okay. There's just a small teensy-weensy issue. I'll redraw the picture in a few minutes because I need the space. I want to set the numerator equal to 0. Okay? So I guess technically this would be true. Kind of stuck, aren't I? Why am I kind of stuck? I have different angles. Oh. I simplified from here to here for the purposes of evaluating this at different angles. Because had I not simplified, you quite literally would have to plug theta in 1, 2, 3, 4, 5, 6, 7, 8 places. That's not incorrect, but man, that's time consuming. So by simplifying it, we made it a lot smaller problem. But we have a problem in that we have 2 different angles. So we're really going to have to go back and factor. Or rewrite this as what? How about if we rewrite it like that? Will this work? Yeah, I'll give you a hint. It's the only way we can answer the question. Is that a fairly easy factorization, by the way? Yeah, I'm just gonna factor out a cosine. And that leaves what? 1 plus 2 sine theta? So this is my, by the way, this is my horizontal. So my horizontal tangent. Because I'm setting my numerator equal to 0. Okay? All right, so what do I need? I need the cosine of theta to be 0. I'll put it up high. Otherwise I'm drifting too far down the page. I need this to be 0, or I need this to be 0. Well, cos theta is 0. We know it, pi over 2, 3 pi over 2, and so on. I only want the answers between 0 and 2 pi. And since those are just thetas, I don't have to manipulate. So let's write them all down. What would this be? At pi over 2 and at 3 pi over 2. And how about this guy? 1 plus, do it off to the side. If 1 plus 2 sine of theta is 0, doesn't that mean sine of theta has to equal -1/2? Okay? Now here's how you be lazy. When is it -1/2? Sine theta, sorry. When is sine theta? Sorry, -1/2. So those are 30 or 60 types with the x-axis. I said, don't go by actually my picture. Sine theta is 1/2. 60 types. But you're in the 3rd and 4th quadrants. So let's give positive angles. So it'd be pi plus a pi over 3. And what would that be? 4 pi over 3? Real quick check. The sine of 4 pi over 3 is -1/2. Or no, I said that backwards. I'm sorry. The pi over 6 is not pi over 3. You were too convincing. Pi over 6 is because I want the vertical to be -1/2. So that would be a pi over 6 type angle. So not 4 pi over 3, but 7 pi over 6 and 11 pi over 6. Quick check. Sine of 7 pi over 6 is -1/2. Boom. -1/2. Okay, boom. I have 4 places on my graph that are between 0 and 2 pi. All right? So let's leave that alone for a moment. Let's now do the verticals. I don't need this. All right, so now we want to figure out where is negative sine theta plus the cosine of 2 theta equal to 0. I can't do anything with this, but I can change this. Now we know there's 3 versions of the cosine of 2 theta. There's cos squared minus sine squared, there's 2 cos squared minus 1, or there's 1 minus 2 sine squared. Because I already have a sine, we want to use the last one. I want to use that one. Now, that doesn't look very friendly. What if I multiply both sides by -1? Then would this be the same as saying 2 times the sine squared theta plus the sine of theta minus 1 is 0? Is that factorable? It's kind of scary looking. How about if I did this? I'm going to be really lazy. Could you factor this one?
Yeah.
Sorry, there's a 2 there, sorry. Well, let's see, I think I'd go 2x and x. I'm pretty sure I'm going to go 1 and 1. So plus, minus, would that work? Is it the exact same thing? Yeah. I'm just doing a little substitution. Sine theta equals x. It's easier to see a quadratic with x's than it is with sine thetas, right? But is it really the same problem? Yeah. I just factored this. So I have two possible solutions.
Two sine theta equals one.
Okay, so the first one, I need sine theta to equal a half. Now, this is where it's always a good idea to draw your unit circle. We did one like this just a moment ago, right? I want the sine of theta to be positive a half, which will happen here and here. Sine of theta is a half when it's a 30 or a 60 type. We just did this a minute ago. When is the sine of theta? The sine of theta can be a 30 or a 60 type angle? The 30 type angle. So the pi over 6, and where else? 5 pi over 6. The second piece says sine theta plus 1 is 0, so sine theta must equal what? -1? And when is the sine of theta going to be -1? Only one place. Where will that be? Three pi over 2? So I have three positions on my graph where I'm going to have vertical tangents. Man, that's a whole lot of stuff going on there, isn't there? It is crazy. Let's see, where can I? I'll draw it over there. I got more space over here. So we did all of this analysis. So we figured out a general formula in its most simplified form for finding the slope at every point. Problem is, trying to work backwards and keep plugging in numbers till I get a 0, that's not very efficient, is it? Now, eventually, might you have plugged them all in? Yeah, but you would have had to do a lot of steps. More than it's worth. So, God, I'd like to make this symmetric if I can. Okay. All right, more or less. Okay, more or less. Okay, well, according to that thing,